right, so in our last video, we were talking about scatter plots and that we were identifying 4 things in a scatter plot. Those 4 things were direction, if it looks like it was going positive or negative, the form or the shape, the structure we see, the strength, how closely the dots are to creating that form or shape, and then are there any outliers, anything weird that we see. So today I really want to focus in on this idea of strength, how closely the dots are to creating a line or a curve. So last time we saw a couple examples, and when we talked about strength, we used some just pretty generic words. It's weak, it's strong, it's moderate. And so I want to give a little more clarity on this idea of strength today. And we measure strength numerically using what's called correlation. Correlation, you've probably heard this word before, but we're going to define it for statistics. Correlation really measures how strong the relationship is. So kind of the shape, how strong it is. A couple things you need to know about correlation. So first off, I have a definition here for you. Correlation measures the strength of a linear association between 2 quantitative variables. Really important things here. Correlation can only be used when our relationship is linear. We're going to discover in Unit 2, linear is very important. Also, something that's often forgotten, correlation we can only do when we have 2 quantitative variables. Thinking back to the difference between quantitative and categorical, our example that we looked at last time about monopoly does provide us these things. Monopoly looked linear, and we had quantitative variables. That's because we had a number of spaces, and we had cost. Those are both quantitative. Correlation is actually independent of the units we use. It doesn't matter if we're in feet or we're in inches. It doesn't matter if we're in dollars or euros. Correlation will come out the same. We use the symbol R as short for correlation. Correlation. You can remember it's an R. And correlation will always give us a number between -1 and +1. So for you little math friends out there, that's how I would say it mathematically. Correlation has to be between -1 and +1. And we will report correlation as a decimal, something like 0.3, -0.85. Those would be our correlation. Now, I love to study correlation because it is probably the most abused, meaning misused, statistical word. It means something very specific. It means the strength of a linear association between 2 quantitative variables. Just for fun, I Google searched news correlation. The first top hit I had was a misuse of the word correlation. Here it is. Study finds correlation between positive mood and yoga. Now, my husband gives me a bad time. He says, oh, the word correlation means relationship. Okay, there could be a relationship between positive mood and yoga, but because we are statisticians, the word correlation does not mean relationship. It means the strength of a linear association between two quantitative variables. Positive mood is not a quantitative variable. You either have a positive mood or you don't. Yoga, that's not a quantitative variable. Either you do yoga or you don't. So, misuse. So just to help you understand kind of what correlation is measuring, here are some visuals. If dots perfectly lie on a line, it gets a correlation, remember that's R, of 1. Now, because this is going in a negative direction, we'll call that a -1. So when something is perfect, makes a perfect straight line, it gets a correlation of 1. The positive and negative signs just tell us the direction. Correlations that are strong, see how these dots are really bunched together? We might get something like maybe 0.8. Okay, really close to 1, but not quite there. Again, notice the negative sign because we're in the negative direction. And then maybe a little more weak These dots are not quite as close and clumpy together. That might be something like a correlation of maybe 0.4, and again, negative, because it's a negative direction. No correlation, I can't see a line there at all. There's a correlation of 0, 0. There's nothing there. Well, there's dots there, but they certainly don't make a line. And then we're going to kind of come around the other direction. When it's positive, remember it's just a positive correlation. Again, weak might be something like 0.3. Strong, ooh, this one looks, it could be maybe 0.9. Okay, getting really close. And again, when it's perfect, we give it a correlation of 1. So that's what I'm talking about when I say it's going to be reported as a decimal. And hopefully you're getting the idea that the closer we are to 1 or negative 1, the better it is. The better it is. All right, so you're probably wondering, how do I actually find the number? And I'll get to that in just a moment. But before I do that, I want to talk about this idea of conditions. For those of you who have taken driver's ed, conditions are like your pre-drive checks. In driver's ed, they teach you you're not supposed to start driving down the street until you've fastened your seatbelt, adjusted your mirror, maybe put your cell phone in the glove box. But there are things you're supposed to check on before you drive down the street. Well, there are some things we are supposed to check on before we calculate a correlation. And those things are right here. Quantitative variables. Make sure you have 2 and make sure they're really quantitative. So in my Monopoly example from last time, I know that the number of spaces is quantitative and cost is quantitative. So I'm good to go there. Is it straight? Well, I've used this interesting word, enough. When I create a scatter plot, does it look linear? That's kind of what I'm asking myself. Or mostly linear? Well, remember our graph from Monopoly. Wow, I mean, it looked amazing. There were a couple of little strange points, but overall it looked great. So we're good to go there. And then outliers. Outliers can do funny things to our correlation. So we just want to check and see if there are any and kind of acknowledge them. And we had, I think it was 3 kind of questionable points. Okay, maybe they're outliers. They were a little weird. Questionable points. So again, just to refresh your memory, I'm referring back to this scatter plot. Okay. Notice I had 2 quantitative variables. I had the number of spaces as my x variable, the cost as my y variable. It definitely looks like I'm straight enough, and I'm acknowledging that there were a few unusual points. Once I've checked those things, then I'm ready to go. I can now look for a correlation. And you may or may not be surprised, we're going to do that on our calculator. All right, so here's my calculator. I'm going to go ahead and just get out. If I go to the Stat menu, I'm going to be calculating. So I'm going to scroll down to option number 8, which is one your book uses. It says lin-reg. I'm not going to explain what lin-reg is today. Just know that that's where we're going. So push enter. And of course, I do need to have my data in here. Mine's already in there previously. I put my x variable in L5. That was the number of spaces, comma, L6. That was my cost. And here's my information. Since I'm looking for correlation, that means I'm looking for this R value. See if I can highlight that there. The R value. So it's 0.877. Wow, judging by the numbers that I gave as example, 0.877 is, or I guess I could round that up to 0.878. That's quite a strong relationship. So again, I might just need to report that. That might be an answer to a question. Being able to report my correlation. The last thing that I'd like to mention is that correlation is not the same as causation. Ms. Curtis, what do you mean causation? By causation, I mean cause and effect. So true story out of your textbook. I just love it so much. The textbook mentions this situation where they kept track of the number of storks. It's a bird. And they kept track of the population in a particular city. I believe it was in England. And they also kept track of the human population. And over time, they noticed this awesome thing was happening. They ended up with this really awesome linear relationship. And it was pretty strong. Very high correlation. Okay, so close to 1. Now, just because there's a correlation does not mean we have cause and effect. It might be very tempting to say, aha, we have finally proven that storks bring babies. Yeah, we've proven it right here now. Unfortunately, that's not the way it works. Okay? Just because I have this nice correlation, okay, something really strong, I don't know, maybe 0.95, it doesn't mean the storks are bringing the babies. There could be another explanation. Real quick, let me give you just one more example. That one was a true story. This one is not based on real data. Just for clarification. Somebody might want to keep track of the number of ice cream cones sold on a beach. And, you know, just for fun, I thought it might be interesting to keep track of the number of drownings at that beach. And believe it or not, I am going to get a positive and pretty strong relationship. Now, does that mean that eating ice cream is going to cause us to drown? No, that's preposterous. That's silly. That's ridiculous. There is another explanation. And in this case, that explanation might be the heat. The hotter it is, the more ice cream cones we sell. The hotter it is, the more people go swimming, which means there's more opportunities for them to drown. So, could be another explanation. Do not get caught in thinking that correlation means we have a cause and effect relationship. Otherwise, you'd have to believe that storks bring babies, and it just doesn't work that way.